Latent spatial memory for video world models. Figure 1: geometrically consistent videos generated by Mirage with latent spatial memory. Given a single input image and a user-specified camera trajectory, left, Mirage preserves spatial consistency by caching 3D information directly in the latent space, rather than as an RGB-colored point cloud. This design enables memory queries through a single latent resolution projection, avoiding the costly rasterize and encode round trip required by prior RGB point cloud memories. Consequently, Mirage can faithfully return to previously observed regions even after large camera detours, while achieving up to 10.57 times faster end-to-end video generation and 5 times lower GPU memory usage than RGB cache baselines. Abstract. Video world models that maintain 3D spatial consistency across generated frames typically rely on explicit point cloud memory constructed in RGB space. This design is both computationally expensive, requiring repeated rendering and VAE encoding, and inherently lossy, as the round trip through pixel space discards rich features of the learned latent representation. In this paper, we introduce latent spatial memory for video world models, a persistent 3D cache that stores scene information directly in the diffusion latent space, avoiding pixel space reconstruction. Building on this, we propose Mirage, a latent space spatial memory framework that constructs the memory by lifting latent tokens into 3D via depth-guided backprojection and queries it by synthesizing novel views through direct latent space warping. This unified formulation eliminates both the information loss of pixel space reconstruction and the computational burden of repeated encoding and rendering. Experiments show that latent spatial memory achieves up to 10.57 times faster end-to-end video generation and 5 times reduction in memory footprint relative to explicit 3D baselines. Leveraging the geometric prior of the diffusion model, Mirage attains state-of-the-art performance on world score and strong reconstruction quality on real estate 10K. Project page aka.ms/latent-spatial-memory. Keywords: video generation, spatial memory, 3D, consistent video generation, video world models. Date: June 8, 2026. 1. Introduction. Large-scale video diffusion models have demonstrated remarkable ability to synthesize photorealistic sequences, motivating their use as world simulators that internalize visual dynamics and generate plausible future observations conditioned on camera trajectories or actions. A central challenge in this paradigm is maintaining 3D spatial consistency. Without explicit spatial memory, even powerful generators accumulate geometric drift, producing frames that are individually convincing but collectively inconsistent when projected into a shared world coordinate system. A natural remedy is to equip the generator with a persistent 3D representation that tracks what has been observed. As shown in Figure 2, recent world generation systems adopt this strategy by maintaining an explicit point cloud in RGB space, which is rendered and re-encoded at every step. While effective at enforcing multi-view consistency, this pipeline introduces two fundamental bottlenecks. First, the repeated round trip between latent and pixel space is computationally prohibitive, as rendering millions of colored points at full resolution and re-encoding them dominates wall clock time. Second, the RGB detour does not preserve the model's native latent conditioning features. RGB point cloud memories render a target view image and then re-encode it into a latent tensor, producing a surrogate conditioning signal that may be distorted by VAE reconstruction error, rasterization artifacts, and distribution mismatch. To address these bottlenecks, we propose latent spatial memory, a persistent 3D cache that stores the diffusion model's latent features at world space locations instead of RGB colors. As illustrated in Figure 2, an observed frame is first encoded into a VAE latent tensor, and each latent grid cell is lifted into 3D by depth-guided backprojection. Each memory element thus pairs a world space coordinate with the corresponding full-channel latent token. At readout time, the cache is projected directly onto the target camera grid at latent resolution with depth-aware visibility handling, yielding a target view latent tensor in the same space consumed by the diffusion backbone. This avoids both pixel resolution rendering of the cache and per step VAE encoding of the rendered image, eliminating the two main bottlenecks of RGB point cloud memories. Building on this representation, we present Mirage, a video world model that generates long, geometrically consistent rollouts chunk by chunk through an initialize readout update latent memory cycle, as shown in Figure 3. First, Mirage initializes the latent spatial memory by encoding the initial frame and back-projecting its latent tokens into the 3D cache via depth-guided lifting. For each subsequent chunk, it reads from memory by projecting the cache onto every target camera pose, producing latent space feature tensors that are injected into the diffusion backbone through a ControlNet-style side branch. After decoding the denoised latents into output frames, Mirage updates the memory by estimating depth, segmenting dynamic objects, re-encoding the frames into clean latent features, and back-projecting them into the cache to preserve geometric coherence. This cycle repeats over chunks to support long horizon generation. Extensive experiments validate the benefits of latent spatial memory in both generation quality and efficiency. Across WorldScore and Real Estate 10K, Mirage achieves state-of-the-art or competitive performance against strong 3D, aware, RGB cache, and video generation baselines. At the same time, end-to-end video generation is up to 10.57 times, end-to-end faster, and uses up to 55 times less GPU memory in 3D cache than RGB point cloud readout, making world-consistent generation practical for long trajectories. Our contributions can be summarized as follows. We introduce latent spatial memory, the 3D memory for video world models that operates entirely in latent space, avoiding pixel space conversion. We propose Mirage, a video world model built around latent spatial memory, with depth-guided back projection for construction, occlusion-aware readout at latent resolution, and iterative refinement with dynamic object exclusion. Figure 2 latent spatial memory versus RGB point cloud-based memory for world model. Top. Prior systems store memory as colored points and pay a rasterization encode round trip at every conditioning step. Bottom. Latent spatial memory stores latent features at world space location and reads them back through a single latent resolution projection, eliminating the per step pixel space detour and shrinking the cache footprint by the squared VAE compression factor. Our method achieves state-of-the-art world generation on WorldScore and competitive novel view synthesis on Real Estate 10K with up to 10.57 times in end-to-end speedup and 55 times in memory reduction. 2. Related work. 2.1 Video diffusion models. The diffusion and flow matching frameworks have rapidly advanced from high-fidelity image synthesis to temporally coherent video generation. Early video diffusion methods extended image architectures by interleaving temporal attention or 3D convolution layers to capture interframe dependencies, while later systems scaled this paradigm to photorealistic, multi-second outputs through large-scale pre-training on diverse video corpora. A common strategy is to operate within a compressed VAE latent space, which significantly reduces the computational cost of the denoising process and enables generation at higher resolutions and longer durations. More recently, diffusion transformers have become the dominant backbone, and various autoregressive and streaming extensions have been proposed to generate longer sequences. Despite these advances, most video diffusion models treat the generation process as fundamentally two-dimensional, in that frames are synthesized sequentially or in parallel without an explicit model of the underlying 3D scene geometry. As a consequence, generated videos frequently exhibit geometric drift, parallax violations, and inconsistent scene structure when subjected to large camera motions or extended temporal horizons. 2.2 Camera controllable video generation. A parallel line of work seeks to condition video diffusion models on explicit camera trajectories to enable controllable viewpoint changes. Representative methods inject camera pose information through additional control modules, epipolar attention mechanisms, or 3D, aware rendering signals fed as conditioning inputs. While these approaches offer fine-grained camera control within a single generation pass, they do not maintain a persistent scene representation across generation steps. Each clip is generated independently of previously synthesized content, so revisiting a region or extending a trajectory beyond the context window of the model may introduce inconsistencies. The absence of a shared spatial memory limits their applicability to long-horizon, exploratory world generation where 3D coherence must be preserved across many sequential generation rounds. 2.3 Spatial memory for video generation. To maintain spatial consistency, a growing body of work augments video diffusion pipelines with explicit spatial memory structures that maintain a 3D scene representation across generation steps. A representative strategy is to lift observed or generated RGB frames into point clouds using estimated depth, accumulate them into a persistent 3D cache, and render target view conditioning images at each step. More recent systems further incorporate long-term context retrieval or surface-indexed view memory to improve temporal consistency over extended sequences. Such memory-based approaches have demonstrated clear improvements in multi-view coherence since the 3D cache anchors each new frame to a shared geometric scaffold. Nevertheless, existing spatial memory designs operate entirely in RGB pixel space, which is both computation-intensive and is vulnerable to accumulated errors in repeated encoding-decoding operations. These limitations motivate our approach, which constructs and queries spatial memory entirely within the latent space of the diffusion model, preserving representational fidelity while eliminating the rendering and re-encoding overhead that constrains prior methods. 3 Preliminaries. A video world model synthesizes a multi-view consistent sequence, I to the power t subscript t equals 1 to the power t, from an initial frame, I to the power 0, and a camera trajectory, e to the power t, k to the power t, where e to the power t and k to the power t are the extrinsics and intrinsics of frame t. Modern systems build on a pre-trained video diffusion backbone that operates in the latent space of a VAE with encoder, E, decoder, D, spatial stride, S, and latent channel count, C. Generation proceeds autoregressively over the overlapping chunk of latent frames, each denoised from Gaussian noise conditioned on its predecessors. Although effective for short clips, this autoregressive scheme conditions only on a small temporal context, so that information about earlier observations gradually fades as the rollout advances. As a consequence, geometric drift accumulates whenever the camera revisits a previously observed region. The same physical surface may reappear at a different position, with inconsistent texture, or with altered scene layout, breaking the multi-view consistency that downstream applications rely on. A common remedy is to attach a persistent RGB point cloud. The set M_RGB contains pairs of 3D points P_I and their corresponding RGB colors C_I. That records the color, C_I, of every observed surface point, P_I. The cache is initialized from I to the power 0 through depth-guided back projection and grown along the rollout, providing a long-term geometric scaffold that the autoregressive context alone cannot maintain. Conditioning on this 3D cache, however, forces a full pixel space round trip at every target view. The cache is first rasterized into an RGB image at the target pose, e to the power t, k to the power t, and then re-encoded into a latent tensor, z caret to the power t, that is supplied to the denoiser. The latent tensor z hat at time t is the encoding of the rasterized RGB mesh, where rasterized denotes z buffered projection followed by shading. This conditioning step introduces two major costs. First, the rasterizer and VE encoder operate at pixel resolution, while the generator consumes latent resolution tensors, making each read unnecessarily expensive and increasingly costly as the cache grows. Second, RGB readout must be re-encoded into a surrogate latent signal, which can deviate from the model's native latent representation due to reconstruction error, rasterization artifacts, visibility holes, and distribution mismatch. Thus, Figure 3 Overview of Mirage. Mirage initializes a 3D latent cache from I subscript 0 by encoding it into VAE latents and lifting them with depth-guided backprojection. At each target view, the cache is read through a latent resolution projection, and generation proceeds chunk by chunk. Each decoded output chunk is re-estimated for depth, re-encoded into latents, and backprojected to extend the cache. Storing memory in pixel space creates both computational and representation bottlenecks for a latent space generator. For method. For point 1 overview. Mirage maintains a persistent latent cache M and generates videos by first initializing memory and then repeating a readout-update cycle over overlapping chunks, as illustrated in Figure 3. Initialization. The initial frame, I to the power 0, is encoded by encoder, E, and lifted into world space via depth-guided backprojection, seeding M, with one latent attributed 3D point per latent cell, section 4.2. Readout and denoising for each chunk, M, is projected onto the target camera grids at latent resolution, producing target view latent feature tensors. These tensors are injected into the diffusion backbone through a ControlNet-style side branch, allowing the backbone to denoise the chunk entirely in latent space, section 4.3. Cache update. The generated frames are re-encoded and backprojected to update M, with moving objects and sky excluded to preserve geometric coherence, section 4.4. Crucially, M is queried directly in latent space, while pixel space operations appear only during chunk-level cache update. This avoids the per-conditioning step render and encode loop of RGB point cloud memories and reduces both readout cost and cache footprint by a factor of S to the power 2. For point 2 latent spatial memory initialization. We represent the memory as a set of latent attributed 3D points. The memory is a set of 3D points, each with a corresponding feature vector, where each point, I, pairs a world space coordinate, P subscript I, with latent feature, F subscript I, drawn directly from the VAE encoder, matching the native input space of the diffusion backbone. Construction. Given a frame with latent tensor, Z is an element of R to the power C times H times W, metric depth map, D, intrinsics, K, and camera pose, E, from a feed-forward reconstructor, we first downsample, D, to the latent grid and rescale, K. Accordingly, in what follows we use D and K to refer to their latent resolution versions. Each latent cell, UV, is then backprojected into world space, producing one memory element per cell. The point P_UV is the inverse projection of U, V, and D, U, V, using K and E. F_UV is a slice of Z, where pi to the power -1 denotes standard pinhole backprojection, Appendix A, and F subscript UV is an element of R to the power C, denotes the latent token stored at the memory element anchored at P subscript UV. The initial cache is seeded by applying EQ to the encoded latent of I to the power 0 and is subsequently updated by the following autoregressive memory update. For point 3 latent space memory readout. Given a target view, E to the power T, K to the power T, we query the latent memory, M, by projecting all memory points onto the target camera grid at latent resolution. For each target cell, we retain the frontmost projected point using Z, buffering, and retrieve its associated latent token, the index of the point with minimum depth, and the corresponding feature vector. Here, omega to the power T, U, V, denotes the set of memory points that project to latent cell, U, V, with positive depth under the target view, E to the power T, K to the power T, and subscript Z, extracts the depth coordinate. Cells with omega to the power T, U, V, equals empty set, are 0 filled. We also produce a binary visibility mask. M to the power T is an element of 0, 1 to the power H times W, indicating which cells receive at least one projected point. This mask allows the denoiser to distinguish genuinely unseen regions from observed regions whose latent feature is 0. This readout preserves the stored conditioning signal, When the cache is constructed from a source frame and queried from the same view, EQ. 5 retrieves the corresponding source view latent tokens on visible cells, up to discretization and occlusion. To generate each chunk, the latent memory readouts, z caret to the power t, and visibility masks, m to the power t, are concatenated and passed to a ControlNet style side branch, which injects memory features into the video diffusion backbone. Besides, segment-aware rotary encodings are also leveraged to mark noisy target, clean preceding, and clean reference frames in a single forward pass. Because the readouts already lie in the backbone's latent space, no bridging encoder is needed, avoiding the rasterize and re-encode step required by RGB cache pipelines. 4.4 Autoregressive 3D Cache Update. After each chunk is generated, Mirage updates M with the newly observed static scene content. We estimate depth and camera parameters for the generated frames using a feed-forward reconstructor, re-encode the frames into clean VA latents, z to the power t equals ei to the power t, and backproject the corresponding latent tokens into the cache using EQ. 4. Then, the updated memory can be denoted as memory M is updated by adding new pairs of position and feature vectors, where lambda to the power t contains latent cells with valid depth outside dynamic objects and sky regions, detected by an open vocabulary entity extractor and a video segmenter. This filtering prevents transient or geometrically unreliable content from contaminating the persistent cache. The current chunk latents are also carried forward as short-term temporal context for the next chunk. 4.5 Efficient adaptation to existing diffusion models. We adapt a pre-trained camera-controllable video diffusion transformer in 2 stages. In the first stage, we freeze the backbone and VAE and train only the ControlNet style side. Table 1 evaluation results on world score. The average score column is the average of the static score and dynamic score, while the remaining metrics are computed by the world score benchmark branch, aligning latent memory readouts with the backbone feature space without perturbing the pre-trained generative prior. In the second stage, we attach rank 64 LoRa adapters to the self-attention projections and jointly optimize them with the side branch, enabling lightweight adaptation to the memory condition while preserving the backbone's appearance and motion priors. Both stages use the flow matching objective on the target frames. 5 experiments. 5.1 Experimental setup. Datasets and baselines. We train on a corpus of videos from Real Estate 10K with depth and camera poses and dynamic regions removed as in Sector 4.4. Evaluation is performed on World Score, which reports 10 metrics covering controllability, consistency, quality, and motion, and on Real Estate 10K, which provides paired ground truth for novel view synthesis and supports the closed-loop protocol of Spatia. On World Score, we compare against RGB point cloud-based scene generators, 12-14, 53, and state-of-the-art foundation video generators, 2, 4, 11, 33-37. On Real Estate 10K, we additionally compare against the view memory baselines SEVA and VMEM, and against 3D-aware video generators ViewCrafter and FlexWorld. Implementation and evaluation. Our backbone is WAN 2.2 Ti2v5b, whose VA has a compression ratio of 4:16:16 and latent channel count, C equals 48. Each generation chunk contains 9 latent frames at resolution, 44:80, corresponding to 33 RGB frames at 704:1280. Training was conducted on 32 A100 GPUs with a global batch size of 64. The ControlNet style side branch is initialized from its corresponding blocks of WAN 2.2 and trained with an AtomW optimizer, float 16 mixed precision, and the flow matching objective on target frames. At inference, we use the UniPC flow scheduler with 40 sampling steps. We evaluate generation quality using the World Score average score and its constituent metrics, as well as PSNR, SSM, LPIPS, and the closed-loop metrics PSNR, subscript C, SSM, subscript C, and PIPS, subscript C. On Real Estate 10K following Spatia. Efficiency is measured on a single NVIDIA H100 with the wall clock time and peak GPU memory for one cache read as rollout length increases. Figure 4 Open Domain Video Comparison. Generations on out-of-domain prompts spanning outdoor and natural scenes that lie far from the real estate 10K training distribution. Mirage generalizes beyond indoor real estate footage, producing temporally smooth and 3D, consistent rollouts under aggressive camera motion, whereas RGB point cloud baselines show stretched textures on unseen layouts and foundation video generators drift in geometry. Table 2 Evaluation results on Real Estate 10K. We report novel view synthesis and closed-loop results. Following Spatia, closed-loop evaluation measures the similarity between the initial frame and the final frame after generating a return trajectory. 5.2 Main results. World generation on World Score. Table 1 summarizes results on World Score. Mirage attains the highest average score of all compared systems, improving over the memory-augmented Spatia baseline and clearly outperforming every foundation video generator that lacks a persistent spatial representation. The advantage is strongest on the dynamic partition, while Mirage remains competitive on the static partition. On the static axis, Mirage leads on 3D and photometric consistency, confirming that latent spatial memory preserves the geometric scaffolding that RGB. Figure 5 Efficiency scaling with rollout progress. Per frame cache read time left and peak cache footprint right, measured on a single NVIDIA H100 across 5 autoregressive rollout chunks. Numbers above each bar report raw measurements in S/frame and MIB, respectively. The y-axis use a linear scale, so the gap between methods is shown faithfully. After the first chunk amortises a one-off setup pass, Mirage settles at a per-frame cost of 0.25s and a cache footprint that grows by less than 0.5 MIB per chunk. RGB cache baselines, Spatia, Gen 3C, require an order of magnitude more memory and 1 to 2 orders of magnitude more time per frame, since every conditioning step re-rasterizes the accumulated point cloud and re-encodes the result through the VE. The view memory baseline VMEM keeps memory bounded, but still scales linearly because its retrieval cost grows with the number of stored views. Latent spatial memory removes the pixel space round trip from the per-step critical path, leaving the conditioning loop with a single latent resolution projection. Caches provide without incurring their representational loss. We attribute this balance to 2 design choices. First, the readout in EQ5 injects geometric hints at the same resolution and distribution as the native latents of the backbone, so the generator does not have to reconcile 2 incompatible signal spaces. Second, the dynamic object filter described in section 4.4 prevents moving elements from contaminating the persistent memory, which is a common source of drift in RGB point cloud pipelines. Figure 4 provides side-by-side qualitative comparisons on out-of-domain prompts, where Mirage maintains 3D coherence on scenes that lie far from the real estate 10K training distribution, while RGB cache and memory-free baselines exhibit visible drift. Novel view synthesis and closed-loop consistency. Table 2 reports results on Real Estate 10K. In the standard novel view synthesis setting, Mirage achieves the best SSM and PIPs while remaining close to Spatia on PSNR, surpassing both view memory baselines and all 3D-aware video generators. The closed-loop setting is particularly informative because it amplifies long horizon drift, since any per-step inaccuracy accumulates over a trajectory that returns to its starting viewpoint. Mirage achieves the best PSNR, subscript C, and SSM, subscript C, under this protocol, while remaining second best on PIPs, subscript C, indicating that latent spatial memory anchors the generator to a coherent geometric representation even after the camera has left and returned to a region. Figures 6 and 7 provide side-by-side video comparisons along the same trajectories. Mirage produces frames that remain sharp and structurally consistent when the camera advances through the scene, whereas Spatia and Voyager occasionally hallucinate incompatible geometry and foundation video generators without spatial memory drift noticeably. Visualizations on more challenging trajectories can be seen in Figure 8. These results show that moving the cache into latent space not only matches a well-tuned RGB cache, but improves on it, because the stored feature vectors carry semantic and textural information that three-color channels cannot express. Efficiency. A central motivation for latent spatial memory is to remove the pixel space round trip from the per-step critical path. Figure 5 plots, as a function of rollout length, the wall clock time of a single cache read and the peak GPU memory required to maintain the cache. We compare Mirage with representative RGB point cloud baselines that rasterizes the accumulated cloud with AZ buffered renderer and re-encodes the resulting image through the VAE at every step. Both quantities grow slowly for latent spatial memory because the read operates at the native latent. Figure 6 video comparison on real estate 10K. Each block shows one real estate 10K trajectory, with rows corresponding to Voyager, Spatia, VMM, and Mirage Rs, and columns showing uniformly sampled frames over time. Across indoor and outdoor scenes, Mirage preserves sharper structure and more stable appearance under camera motion, while baselines exhibit geometry drift, texture distortion, or accumulated artifacts. Figure 7 closed-loop revisit comparison on real estate 10K. In the closed-loop test, the camera trajectory gradually returns to its starting point. The comparison between the last frame and the input frame shows that Mirage maintains strong consistency under the revisit setting. Resolution and the cache itself is smaller by a factor of s⁻², per spatial dimension. In contrast, the RGB cache exhibits rapid growth along both axes, since the per-step rasterization scales with HW rather than HW, and the cloud expands roughly linearly with the number of anchored frames. At matched rollout length, end-to-end video generation is 10.57 times faster than the RGB pipeline and consumes 55 times less GPU memory on 3D cache. The gap widens with Horizon, and RGB baselines eventually exhaust the memory budget on trajectories that latent spatial memory completes comfortably. 5.3 Ablation Studies. We isolate the contribution of each component of Mirage on a split of world score prompts, so that ablations are directly comparable to the main benchmark. Component-level results are reported in Table 3, and the sensitivity to the depth source used to build the latent cache is reported separately in Table 4. Latent versus RGB memory. Replacing the latent cache with an RGB point cloud of the same source frames, while keeping the backbone and training recipe unchanged, decreases the average score and weakens 3D and photometric consistency. This confirms that bottleneck of the RGB detour discards information that backbone can exploit when the cache remains in latent space. Feature downsampling versus geometry downsampling. An alternative to the design in EQ is to upsample the latent feature to pixel resolution and lift at full resolution, then aggregate into the latent grid during readout. This variant degrades 3D consistency because it interpolates features that lie outside the backbone's pre-training distribution. Matching geometry to the native latent grid instead is both cheaper and more faithful to the generator. Dynamic object filtering. Disabling the mask that excludes moving objects and the sky from cache updates degrades long horizon stability, since stale dynamic content persists in the memory and is splat back into future chunks. The effect is largest on 3D and photometric consistency. Two-stage training. Replacing the two-stage schedule with a single stage that jointly trains the side. Table 3 Ablation Studies on a world score split. Each row disables or alters a single component of Mirage, while all other settings remain fixed. Table 4 Sensitivity to the depth source. We swap depth anything 3 for alternative depth predictors while keeping all other components of Mirage fixed. Branch and LoRa reduces final quality because the backbone adapts to an immature conditioning signal early in optimization. Freezing the backbone during stage 1 and only then unlocking LoRa stabilizes convergence. Depth source. Because latent spatial memory is constructed from estimated depth, we study its robustness by swapping the default depth anything 3 reconstructor for alternative depth predictors. Table 4 shows that Mirage remains competitive under noisier depth, because the ControlNet-style side branch treats the projected cache as a soft geometric hint rather than a hard constraint. And the dynamic filter removes the worst outliers before they enter the memory. The margin relative to the strongest depth estimator is modest, indicating that the benefits of latent spatial memory do not hinge on a particular reconstructor. 6. Conclusion. We have introduced latent spatial memory, a 3D cache that stores the video diffusion model's own latent features rather than RGB colors at each world space point, and built Mirage around this representation as a video world model that operates entirely within the VAE latent manifold. By reading the cache through a single latent resolution projection, Mirage removes the rasterize and encode round trip that dominates the per-step cost of RGB point cloud caches. The decode and re-encode pair required to grow the cache is amortized over an entire chunk and never appears in the conditioning loop. So the per-step critical path is freed of pixel space operations and the cache footprint shrinks by the squared VAE compression factor. Across World Score and Real Estate 10K, Mirage delivers state-of-the-art quality while reading from the cache an order of magnitude faster and with an order of magnitude less GPU memory than RGB cache baselines, turning world-consistent generation into a process that scales with the rollout horizon. Limitations and future work. The dynamic region filter excludes moving entities from the persistent memory because their geometry is unreliable, so Mirage does not maintain the state of dynamic actors across chunks. Scenes dominated by pervasive motion therefore benefit less from the cache than scenes dominated by rigid geometry, and persisting dynamic content across chunks is a natural direction for future work. 7. Acknowledgements. This work was supported by computing resources from Microsoft. Geometric details. This appendix spells out the geometric quantities that the main text defers, so that section 4 stays readable while the construction in X 4-6 remains fully reproducible. Conventions. Extrinsics. E subscript T is an element of SE3, map world points into camera T, and we denote the camera towering inverse by E subscript T to the power -1. Intrinsics follow the standard pinhole form with focal lengths f subscript x, f subscript y, and principal point c subscript x, c subscript y. The VA has spatial stride s, dividing the pixel resolution h times w into the latent resolution h times w equals h/s times w/s, with s equals 16 throughout. Appendix C. Latent cells are indexed by v is an element of 0, w-1 times 0, h-1 with pixel center homogeneous coordinates u plus 1 over 2, v plus 1 over 2, 1 to the power downtack. Latent resolution intrinsics. The latent resolution intrinsic matrix used in X 4 and 5 is obtained from the pixel resolution intrinsics K by scaling both axes by the corresponding stride ratio. The latent resolution intrinsic matrix K superscript L is a diagonal matrix multiplied by K. Both focal lengths and the principal point are rescaled by the same per-axis ratio, so that perspective projection remains consistent after the depth map is downsampled to latent resolution. In the main text, we slightly abuse notation by writing K4, K to the power, wherever the context is unambiguous. Pinhole back projection. The operator, pi to the power -1, used in EQ, for maps a latent cell, UV, with depth d equals d, u, v, into a world point through raycasting in camera coordinates followed by the camera-to-world transform. The inverse pinhole projection maps a 2D point with depth to a 3D world point using camera intrinsics and extrinsics, where the trailing subscript denotes selection of the first 3 coordinates. Projection onto the latent grid. For a memory point, P subscript I, its camera space position at target view T is the first 3 coordinates of E subscript T P subscript I to the power downtack, 1 to the power downtack, which we denote. Q subscript I is an element of R to the power 3. Its position on the latent grid is then the 2D projection of a 3D point onto a latent grid using a camera matrix and depth normalization. The candidate set used in the readout of EQ, 5 is then the set of indices $I$, where the projection of point $Q_I$ is $U, V, and its z-coordinate is positive. And the admissible cell set, lambda subscript T, in EQ, 6 is defined on the same grid, restricted to cells with finite positive depth that lie outside the dynamic object and sky masks. The additional experimental analysis. This appendix complements Section 5 with analyses that clarify why latent spatial memory is efficient, how it behaves as the rollout horizon grows, and what the stored tokens carry compared with an RGB cache. Asymptotic cost of cache reads. Let n denote the cache size at a given step. Reading an RGB cache costs theta n log n plus hw plus theta phi subscript e hw per conditioning step, where phi subscript e is the flop count of one VE encoder pass. Reading a latent cache costs theta n log n plus hw, the rasterization term shrinks by the squared VAE stride, and the per step encoder term disappears entirely because the readout is already in the backbone's input space. The peak memory of the cache itself follows the ratio s to the power 2, 3/c between the RGB and latent representations, which together with the per step. Figure 8 additional video comparison on a challenging indoor trajectory. Mirage maintains coherent layout over the full trajectory, whereas baselines suffer from view-dependent deformation, blur, and inconsistent scene reconstruction. Table 5 depth downsampling for cache construction. Evaluated on a held-out real estate 10K split with every other component of Mirage kept fixed. Pixel resolution buffer accounts for the order of magnitude gap reported in Figure 5. The gap widens with the rollout horizon. The n log n sort begins to dominate the latent cache much later than the pixel cache, and the RGB baseline exhausts GPU memory on trajectories that Mirage completes comfortably. Per step timing breakdown. We decompose the per step cost of the RGB pipeline into rasterization, VAE encoder forward, and depth estimation plus back projection. On a 257-frame rollout, rasterization and the encoder together account for more than 98% of the per step RGB cost, and both are absent from the conditioning loop of Mirage, since a single latent resolution projection replaces them. The decoder, which the RGB pipeline calls at every conditioning step to produce the image on which the cache is rasterized, is invoked in Mirage only once per chunk to materialize output frames and to feed the depth and segmentation modules. It never appears on the per step critical path. Depth downsampling for cache construction. EQ requires the dense depth map and the latent grid to share a resolution, so depth must be downsampled before lifting. Because depth is piecewise smooth with discontinuities at silhouettes, this choice is not neutral. Bilinear interpolation smears foreground over background at edges and can spawn phantom points. Nearest neighbor preserves edges, but aliases fine structure. Area pooling oversmooths occluding contours. Median pooling preserves edges, but is biased on slanted surfaces. We evaluate all four with every other component fixed. Table 5 reports the fraction of empty latent cells in the projected cache whole rate. Among the four downsampling choices, bilinear interpolation gives the lowest whole rate at 42.53%. We therefore adopt bilinear as the default, since it provides the best projected cache coverage among the tested variants. What the cache stores. The latent tokens are expected to carry semantic and textural structure that 3 color channels cannot express. We visualize this by projecting each per-point feature vector onto its top 3 principal components and coloring the memory by the resulting RGB. Coherent semantic clusters such as walls, floors, windows, and furniture emerge that are not recoverable from an RGB point cloud built on the same frames. This is the qualitative mechanism behind Table 3, where swapping the latent cache for an RGB cache with the backbone and training recipe held fixed weakens both 3D and photometric consistency. See implementation details. Backbone and latents. The backbone is WAN 2.2 Ti2v5b, whose VA has spatial stride S equals 16, temporal stride 4, and channel count C equals 48. Each generation chunk covers a 9 by 44 by 80 latent tensor corresponding to 33 RGB frames at 704 by 1280. The transformer has hidden dimension 3072, feed-forward dimension 14336, 24 attention heads, 30 blocks, text context 512 tokens, and uses RMSQ/K normalization together with cross-attention normalization. The V is frozen throughout. Conditioning branch. The latent readout, Z-subscript T, is injected through a ControlNet-style side branch whose layout mirrors the base blocks of WAN 2.2 and shares its patch embedding with the main network. The branch is attached at layers 0, 4, 8, 12, 16, 20, 24, 28 with a 48 channel input matching the VAE latent, so no bridging encoder is required. Segment-aware rotary positional encoding tags each frame as noisy target, clean preceding, or clean reference inside a single forward pass. At inference, the denoised latents of the previous chunk become the preceding frames of the next. Training. Training has two flow matching stages on the target frames. Stage 1 updates only the side branch at learning rate, 10 to the power minus 5, with the backbone and VAE frozen. Stage 2 unlocks rank, 64 LoRa adapters on the Q, KV, O projections of every self-attention layer, alpha equals 64, dropout 0.05, and jointly optimizes them with the side branch at learning rate, 10 to the power minus 4. Optimization uses AtomW, beta equals 0.0, 0.999, weight decay, 10 to the power minus 3, a cosine schedule, float 16 mixed precision under FSDP sharding, gradient checkpointing, and text dropout probability 0.2. At inference, we use the UniPC flow scheduler with 40 steps and classifier-free guidance disabled. Efficiency is reported on a single NVIDIA H100. Data. Training clips are drawn from Real Estate 10K. Each clip is processed by a feed-forward reconstructor for metric depth, intrinsics, and per-frame extrinsics, and by a Qwen3 VL2B entity extractor followed by SAM3 for foreground dynamic and sky masks. Cells inside the mask are excluded from lambda subscript T in EQ6 so that only geometry compatible with the rigid scene assumption enters the persistent memory. Frames, latents, depth, and camera parameters are stored in an LMDB-backed dataset, so no re-encoding occurs during training. Rollouts are produced in chunks of 9 latent frames with 1 frame overlap to preserve temporal continuity, and the cache is grown once per chunk by re-encoding the decoded frames and lifting them via EQ4. Algorithm 1 summarizes one complete rollout. Equal contribution.